keynote speaker for this afternoon. I'm really grateful to him for agreeing to give this presentation. He has a PhD in electrical engineering and a background in signal processing, but he's not typically, I don't think he considers himself a member of the computational imaging community. So he's essentially doing us a favor by being here. At the moment, he's a data scientist at the Berkeley Institute for Data Science. But to you, he's probably most well known as the founder of Scifi Image, and he's also very heavily involved in the Python scientific computing community. He's often seen at Sci-Pi conferences, for example. So as I said, it's a real pleasure to have him here. So thank you, Stefan, and please get going when you're ready.
Thank you very much, Brent. And hello, everyone. It's great to be here with you this afternoon, evening. So yeah, thanks for this opportunity to talk to you more about developing open source scientific software, specifically in Python. We had a panel discussion about this morning, a little bit about the challenges around adopting open source tooling for computational imaging. That was very enlightening. And I got the general sense that there's quite an appetite for adopting these tools, although there are many uncertainties about the exact hows and whys and the barriers that one might run into. So hopefully this talk can answer some of those questions. But if not, I plan to leave some time at the end of the talk for further discussion. Right, so before we get going, just some context. I've been working in the scientific Python ecosystem now for around 15 years, and therefore my perspective stems primarily from this work in scientific Python. But many of the points I will be making are more generally applicable to open source in scientific computing. But that's at least my background coming here. So in this talk, I hope to convey the following 3 points. I hope to show you that open source is the right fit for science, that really that is the way we should be thinking about software for this purpose, for open verifiable computation. I want to show you that the core packages are reliable and that they are continually improving, that they've got processes in place for improving, so you can rely on them improving over time. And then finally, that we all will benefit by supporting this commons, this resource that we've built that has become very valuable to so many fields. So I'm going to give you a brief history of the Scifi project, because the Scifi project is tied closely to the scientific Python ecosystem, sort of the seed that started all of it. And we start off around 1991 when the Python language arrived. Python was designed as a teaching language, as a language that's very easy to understand, to read, and was meant to facilitate rapid prototyping. But very importantly, it was a general purpose language. It was not developed specifically with science use in mind. It's a generic language that people eventually repurposed for science, but there were no specific scientific data structures or algorithms. So around 1995, numeric arrived. That was the first library that supported array computation, and that initiated the rapid growth of small numerical packages for Python, tiny utility libraries that touched on various use cases. Around 2001, the first version of Scipi came out. So this was basically a bunch of grad students who had wrapped existing Fortran libraries, and they brought their efforts together trying to build a slightly larger package with broader functionality. So that happened around 2001. That was also around the time when the first version of IPython came out, Interactive Python, and that package was also written by grad students, and that is what eventually developed into what is now known as Jupyter. Around 2002, then, was the first Scipi conference. This was a single track event, 2 days, 50 attendees, very small group. But this also signaled the start of adoption of these utilities in the national research facilities and laboratories. And then around 2006 was a major milestone for the community when the first version of NumPy came out. So NumPy put together the best aspects of, by then, two existing array libraries, numeric and numarray. One was aimed by the astronomy community, aimed at processing very large images. And by blending these two together, they came up with what is now NumPy and what is the widely used array processing library for Python. So this was really the moment where people started to see, like, there's now one obvious way to get into this, and they started running with it. In 2008, we launched the SciPy documentation project. So the NumPy was mostly undocumented and to a large extent untested at this point in time. So it was really still immature on some levels. And this documentation project then allowed us to document the library. In the first summer, we did NumPy, and the second summer, we did SciPy. So after that, the whole ecosystem was more or less covered. And that greatly increased people's ability to engage with these packages and use them. So I'm going to jump ahead then by about 12 years, and that brings us to today, where you have 600,000 lines of code. It's organized into 16 sub-packages. You have 110,000 GitHub repositories, depending on this project, 6,500 libraries, depending on SciPy. And with the SciPy conference having over 1,000 attendees, with the latest virtual conference was 1,400, and 3 parallel tracks running. So it became hugely popular. But this gives you a sense of sort of the timeline, the duration and time that it takes to develop packages like this, and also a whole community around it. So if you're interested in this history, you can read more about it in our SciPy 1.0 paper. That one, I'll show you in a second where that one is published. Yeah, so if you're interested in further reading, there are several papers out there. Many of these projects have their own papers published. The ones I showed here, there's a NumPy paper that recently appeared in Nature. Nature Methods has the SciPy paper, and I show the scikit-image and the scikit-learn paper. And it's kind of interesting because software developers don't normally write papers, but here you have this intersection between scientists and programmers. So yeah, obviously they publish their work. But interestingly, it also shows that there's a wider scale realization of the fact that these tools are really becoming critical infrastructure, and that they are of huge importance to moving science forward. That's an important milestone for the ecosystem. So since this is an imaging conference, I want to show you things that tangentially touch on that. So here are a few examples in that space. So scikit-image is a project that I've been involved with. I founded in around 2010, mainly as a place to put the algorithms developed as part of my PhD, also to gather all the algorithms that were posted on the SciPy mailing list. But from then to now, we've had around 500 people contribute to the package. And if you're not familiar with this ecosystem, the scikits are more or less like MATLAB toolboxes. So anyone can build and publish one. In the scientific Python ecosystem, packages tend to be bigger, larger, so they tend to aggregate. So you have SciPy, which contains a whole bunch of routines. But then sometimes it becomes beneficial to have a smaller group of developers come together, start their own project, rapidly iterate, and set their own development agenda. And that's what happened with some of these packages like scikit-learn and scikit-image. The image pics that you see here, these are from our online gallery that you can visit at scikit-image.org. And I just kind of randomly chose 2 of them. But you get a sense it's a bunch of image processing algorithms that you can use as fundamental building blocks to build your own extended pipelines. This image made a big splash over the last year, and it is evidence that there is an increasingly large volume of science that was enabled by these tools that we're building out in the open. And this image, it may be one of the most popular images of the past year. It's the very long baseline interferometry reconstruction of M87 Star. That's a black hole at the center of Messier 87. It's got billions of times the mass of the Earth's sun, and is an enormously important scientific milestone. And when you look at the software that was used to construct this image, then you see that, so this is EHD Imaging. It's Andrew Chale's library. And if you look at the list of requirements, you can see that almost all of those libraries come from the core of the scientific Python ecosystem. And that means that these are packages that were developed by the community for the community, written by students, researchers, scientists for their own use and for the use of their peers. We really have here a community of practice, people who come together for a joint purpose and who learn together to be better at what they do, and then put that knowledge back into this ecosystem of tools that we're building. Finally, this is a screenshot of Nepar. So Nepar is a graphical image viewer that you can use to inspect data sets. It integrates very tightly with other scientific Python tools. And what I love about Nepar is it's got a beautiful, clean API, and you can drive it from an interactive interpreter. Because it integrates with Dask, a distributed computation library. You can use it to view and operate in very large data sets in any number of dimensions. So what you see here is a three-dimensional view of a 125 gigabyte four-dimensional array, X, Y, Z, and time. And it's loaded live from disk using the ZAR library. But this is absolutely typical of the scientific Python ecosystem. You have packages that communicate with one another, talk to one another, integrate really well, and you can put them together into these very sophisticated pipelines. Here's another Nepar example. So what you're seeing here is a neural network being trained, and at the bottom of the screen, there's a matplotlib plot embedded showing you the loss function, and then you can interact with the training output as it is being generated. So in this example, we combine matplotlib at the bottom, PyTorch for the neural network training, and Dask for organizing the training workflow. So again, several packages coming together to give you this very useful utility. Right, so I mentioned that I want to discuss these 3 points. So I'm going to start with this one, so that open source is the right fit for scientific software. I'm very curious who will remember these devices. So when I was young, my dad had a copy of AutoCAD that I liked to play with. But I remember that every time he would go to work, AutoCAD would not run. And the reason was that he had this dongle, the software protection dongle that you had to put into the parallel printer port in order to make this piece of software work. Later on, when I was in grad school, we had MATLAB licenses, but in order to use these, you had to access the license server. And if the license server was down or anything was wrong with it for some reason, you couldn't access your software. And I thought, this is silly, this is ridiculous. So I switched over to Octave back then. And for some of these packages, you need one license per CPU core that you're using inside of your cluster. So can you imagine the nightmare in trying to get that organized? Also, each part of your workload needs access to the license server, otherwise it can't even execute. But this is the kind of stuff I have no patience for. I don't want to deal with at all. And it made me realize that clearly we need control over the environments that we use for our computation. So this is then when I want to compare commercial and open source software, there are various axes on which you can do that comparison. And so there's ownership. I feel like it's really important that scientists are able to steer the development of the software they use, that they're able to collaborate with one another in building the tools they require, to inform the development, to make sure the tools best fit their own use cases. But this isn't possible in a commercial setting. In Africa, where I grew up, cost was always a factor, and commercial software was often free at the university, but the moment you left the university door, then you had to pay for that university. So you had this very bad situation where people would get trained in a piece of software that they later either can't afford or have to buy licenses for. And that situation did not seem like a good one. But it goes beyond that. So do you have access to the system when you need access to it? So can you deploy the system you wrote onto a Raspberry Pi or a server in the cloud or under any setting imaginable under the sun? Or do you have to ask permission every time that you want to do that? In terms of implementation transparency, we're working on science here. We want our software, our whole research stack to be transparent so that people can go in, look under the hood, and verify the work that was done. And this is not possible with closed systems. The above two items, so access and implementation transparency, those two come together. Without them, it's very hard to have good reproducibility. And then finally, in terms of interoperability, if you have a bunch of systems that you're tying together, and this happens all the time in data science where you have these complex pipelines that you construct. If you build them out of closed components built in a silo, it's very unlikely that these systems will communicate effectively with one another. But in the open source ecosystem, that's not the case. We'll talk about that just more in a little bit. And then finally, the question, like, what is the focus of this package, and does it serve the needs of the community? And I would venture to say that all these points are addressed by open scientific software. So we have ownership of the open software. We can steer it, it's community driven, and contributions are accepted online. We have access to it. These packages are all released under liberal licenses, and you can apply it in any way you choose. The licenses guarantee that you have that freedom, and there's no charge involved, so no money changing hands. The implementation is absolutely transparent. Everything is online. You can read the code, you can modify it. Like I said, reproducibility you get when you have these two things. When you have access to the software and when you have the ability to introspect the software, then you have a reproducible system because you can give it to someone else, they can deploy it on their computer system, and they can verify if something goes wrong, they can go and look what is the reason for that thing going wrong. In terms of interoperability, because most of these tools are open and in the same ecosystem, they have to be able to talk to one another. That's the only way in which this functions. And the focus ultimately, well, in the case of open software, there is no profit incentive. So the goal there is to collectively address the needs of the scientists and the community. So my strong takeaway from this is that scientists must absolutely own the software that they wish to use. Okay, on to the second point. So I'd like to demonstrate that the core packages are reliable and that they have processes in place for improving over time. Because as absurd as it might seem to some people, there's sometimes you get this question like, can high quality software be constructed outside of a commercial setting? And of course, absolutely, yes, it can be done. So these are attributes of projects in the core of scientific Python. So they are mature projects. They are developed in the open. The community is involved with these projects. They drive the development, but they also govern the project, so they get to make the decisions and the decisions about who makes decisions and so forth. The project is well documented, so it can be used. It's well tested, liberally licensed, and plays well with the other libraries in the ecosystem. A central goal of open source software is that it must be reliable and usable. The developers in this case are also the consumers, so it is important to them that the software must be usable. So as they develop it, they keep this in mind. It might be them, it might be their students, it might be their colleagues, but the focus is always on what are we doing for the community here. You often get, so the group that develops these packages, it's a self-selected group, volunteers, and they often arrive at the scene with great skills. Like the community here, they may be some of the most talented people I've ever worked with, and I've certainly learned more from them about programming than from anywhere else. Just an extremely talented bunch of people. And they're there because they want to be there. They're there because they need to develop these tools for their own work. The incentives are absolutely aligned with the development that needs to take place. So there's an interesting forcing function that happens in open source. I think a lot of other groups are running into that right now, where they have to organize to collaborate in a remote fashion. But for open source, this has always been true. So we're distributed across the globe. We don't always work in the same time zones, so we're awake different times of day. And you sometimes have people leaving the community and new people coming in, and that turnover can be quite rapid. And all these things together create an environment in which we are forced to write software that is very readable, that is well documented, that is automated. The testing, the systems around it have to be automated to the extent possible, and you have to make sure that whatever goes in is read, is reviewed, is of high quality. Otherwise, you simply cannot have that kind of asynchronous development happening in space and time. So let me run through those points each. So readable code. Python here is fantastic because the language was designed from that principle of having to be highly readable. And here's a classic adage that says, indeed, the ratio of time spent reading versus writing code is well over 10 to 1. We're constantly reading old code as part of the effort to write new code, and therefore making it easy to read makes it easier to write. And this is something you run into even more often with open source development. You may hand over a piece of code today to someone that you don't know tomorrow, and you cannot rely on institutional knowledge to carry forward. So you basically have to make sure that this is documented in some way so that the other developers can follow. And this leads, for example, you can draw various conclusions from that, but one outcome, for example, is that in the scikit image values, we say we value simple, readable implementations over getting every last ounce of performance. Readable code that is easy to understand for newcomers and maintainers alike makes it easier to contribute new code as well as prevent bugs. And this means that on a practical level, we will prefer a code that is slightly slower if it reduces the complexity or the number of lines of code. In terms of documentation, it is very important to us that the documentation is consistent throughout a single package, ideally also across the different packages, although that kind of coordination we're still building up in the ecosystem. But at least within projects, it is clear that you need very consistent documentation. But at least in the scientific Python ecosystem, there is a standard. The standard for documentation was developed by the community. So you'll see, I show you on the side, a typical doc string, documentation string from scikit image, and you can see that there's a set format. So there's a single line description of the function, then a paragraph that describes it, and then we have the input parameters, the output parameters, the returns, maybe some notes on the implementation, some references from papers, and then some code examples that people can use. And this is the format we use for every single function in the library. And we do not consider this optional. You cannot contribute code into this library without providing said documentation. It just won't be accepted. And that way we make sure that users have access to what they need when they're trying to apply the library. Moreover, these changes, every time that you make a change to the documentation, it's compiled and all the code snippets are executed and the build artifacts are provided to the person who made the change. And once these changes have been integrated into the package itself, the documentation automatically updates online. So these two things are always in lockstep. The documentation is available online, but it's also available inline in many environments. So if you use an interactive prompt like IPython or Jupyter, then you can very easily pull up these sets of documentation, and they appear right there where you need them. And then we also have a lot of gallery examples. Those are used to provide use cases of the library, but not attached to any specific function. But you may have a denoising gallery example that shows how to apply various kinds of denoising, or a radon transform, or whatever it might be. But importantly, what I want to highlight here is that the community designed the format. The community built most of the tools that are being used here. So they have the parser for the documentation format. They wrote the software that generates the HTML, the PDFs, and now there's a variant of the markup language designed by the community. This really is, as I said, a community of practice where people come together, learn what works, and then improve upon that and iterate over and over and over again. And that process over time results in market improvement. So finally, automated testing. Those of you who work in software will be familiar with this, but every time that you make a change to any of the core packages, a continuous integration server is used to take those changes, compile them into the package, and test them. So you propose a change, we run automated checks to make sure that the change doesn't break anything. We also require that new tests accompany new functionality. So if you bring a new piece of functionality, there is a piece of code that ensures that it does what it's supposed to do, that it's accurate. And once all those checks have passed, you get these green check marks that you see on the screen. And then we require that two developers of the package go and review the code line by line. They will typically comment on it, but we'll get to that just now. But once they've approved, the changes can go in. But this automated testing is an absolutely crucial step into making sure that the software is of high quality. So here's the iterated peer review process that I just mentioned. So this is sort of the lifetime of a change as it gets submitted. So if you're familiar with GitHub and with Git, you start a branch. So you basically split off the software. You make your own changes to the software. We call those commits. And then once you're ready, once you're satisfied with the changes that you're going to propose to the package, then you make what we call a PR, pull request. That allows the rest of the developers to then come in, look at the changes you propose, and they will comment on it. And you then take the recommendations and you can discuss it, choose to reject it, or work with the developers and try and integrate those suggestions into your change set. So there's a conversation going on, and this conversation happens over several iterations until at least two of the core developers are happy that the proposed change is in an acceptable state. Generally, we work on a consensus basis, so everyone is interested, is satisfied with the change, and then it gets merged into the master branch of the package itself. And at that point, again, all the tests are run, and the documentation is built, the website is updated, and so forth. Right, so that concludes that previous slide then around readable code documentation, automated testing, and iterated peer review. If you're interested in that topic, I recommend this chapter in a book. It's by Millman and Perez, Developing Open Source Scientific Practice, and that appears in Implementing Reproducible Research. So just to recap, if you have peer-reviewed software combined with good programming practices, and you rely on automated checks whenever possible, it ensures that your code is likely to be correctly implemented, give accurate results, and that it will be easily usable through high-quality reference documentation. So finally, I want to discuss what we can do to support this commons. We've built this rich resource, this software built by the community for the community. What can we do to support this software and to help the ecosystem grow. So open source software can very easily sustain itself at a small scale, but as these projects grow and become larger, more resources are typically needed. And by that I mean both financial and human. You need that in order to ensure that the incoming work proposed can be integrated, that you can make new releases, that infrastructure used can be kept up, and that you can do coordination between the different projects as necessary. But it is absolutely to our own advantage to own our software, as we saw, and therefore also to upkeep our own software. And I think if commercial models are workable in the academic world, then there's absolutely no reason why we can't apply some of the same resources towards open software development with greater benefit in the long run. And I have to say that there's been a change in the funding landscape as of recent, and we've seen that foundations like the Chan Zuckerberg initiative with their Essentials of Open Source Software program, the Gordon Betty Moore Foundation, the Alfred P. Sloan Foundation, Heising Simons, all these foundations have really come through and have started to look at how they can support these projects because they don't see a lot of support from elsewhere. NASA recently announced its first grant for this type of thing, so we're very excited to see that. All right, so what can you do then? And I guess this depends a lot on the context you're coming from. My reference is somewhat biased to the academic side of things, but you can, of course, do the most straightforward thing, which is to maintain a package in the ecosystem or take up one of the many roles that are available. If you are a teacher, you can teach using these open source packages so that your students will learn to use them and hopefully take them along as they progress. Excuse me. You can advocate for these open packages. There are many places to do that. You can support graduate students because, as you heard, most of these packages were developed by graduate students, and they need to be supported in various ways. They need to be taught how to use the tools, and they need to be allowed to work on this and not only focus on grinding out papers, because this is an important academic output as well. When we review papers, we have to make sure that we review for transparency. So if people say that they wrote a piece of software, where's the software? Have them place the software online and show it, or otherwise make an explicit statement that they're not willing to open up the software. Because ultimately, scientific software should be open for introspection. We need to be able to verify that what is being said about the software is true, and the results derived from the software represent a reasonable estimate of the real world. And then, of course, you can fund development directly, but not everyone's able to do that. And then finally, if you have cloud with any of the funding agencies, let them know how important it is to support this critical infrastructure. And I just wanted to mention this interesting phenomenon. So there's a forum that was constructed by the biological imaging community recently, the microscopy community, I would say. And they brought together for the first time open source packages across languages to all talk to one another as practitioners in one field of focus. We haven't seen that before because mostly these efforts, the forums and the discussion places, are all clustered around specific languages or even specific projects within those languages. So this was the first time that I'm aware of that we brought people together from such a diverse background. It's been really interesting because we've been able to learn from one another about what the needs are in the various ecosystems and the gaps that are, the gaps and the opportunities that are available. And I think also like inspired one another to use better practices and be better at the work we do. And so there's a question in my mind as to whether there's an opportunity here for the computational imaging community also to come together and to organize around what their open needs are and what can be done to improve the software in that space. And this focus is all possible with initially volunteer effort and eventually, hopefully, some more resources and time. So to conclude, open source gives us the freedom to jointly develop software that best meet the community's need. It also lends greatly needed transparency to science, and thereby it facilitates work that can be inspected, verified, and reused. When developed well, open source can be of extremely high quality. And then just finally, this reminder that open source is free, as in freedom. You can repurpose it, use it for whatever your needs might be, but there is still a significant cost to open source development, and it requires resources to develop. So we should support these projects in whatever way we can to ensure their long-term viability, and so we may continue to benefit from them in the long run. So that's what I have. Thank you very much for listening. I'm very curious to hear your questions and comments. You're welcome to disagree from me on any of my opinionated statements that I made. Be happy to hear your thoughts. Thanks very much.
Thank you, Stefan. Right. Any questions? While I'm waiting to see someone raising their hand, I have one. Given your experience in this area, what's your advice on the best way of putting a team together to actually build software? In the sense that, and so this is a computational imaging conference, but let's make it a little broader let's broaden it a bit to signal processing. And typically, signal processing people don't have a great background in software development. So if I have a team that I'm trying to put together to build some tool we realize we need, should we be trying to teach signal processing people to be better software developers, or should we be hiring software developers and teach them enough signal processing so that they can write the code to solve our problems?
That's a fantastic question. Very relevant. Yeah. It's also not the easiest one to answer, but I think part of the answer comes from the agile space. And what they've seen there is that every time you have handovers, you introduce great inefficiency. So if you have a group of field experts who try and describe a problem, and then you have a separate group of people responsible for software development, the interface between those two would be a point of contention. So really, I think ideally, the community would own their software. So you definitely need to work on over time leveling up your own developers in the community, and we're trying to make that easier and easier over time inside of the Scientific Python ecosystem. There's a great focus on improving onboarding and making it easier. But despite that, if that's not entirely possible, bringing people from the software field into the fold is probably a good idea. As long as they're part of the teams. So if you have a unified team, that team consists of both a field expert, a statistician, and a software expert, that team together can make a big impact in this space. And in many ways, I think that's the way that labs should be organized. We have these very strange structures. We have like the PA and the PI and everyone underneath. But I think we need to be focusing on these teams that have wider expertise and then can work together towards scientific solutions. And I think those teams can make a big difference. Tying that back to scientific Python development, we've started recently to focus on expanding our roles, because we realized that essentially we just had one role, which is like core developer. And we ran into problems because of that. You need wider input in order to be effective on all the different places. So yeah, it's not easy. I understand what I'm saying is kind of a departure from what's existing in academia and often in the labs. But yeah, I don't really see another way around it.
So to expand on that, for example, given the core scikit image developers, what fraction of those are imaging people or image processing people, and what fraction of them are software developers? What's the balance?
Yeah. So originally, at least, everyone who worked on SciPy did so because they needed the tools in their own work. And later on, you had computer scientists and others coming along who were interested in sort of meta aspects of the project. But it definitely started out as a project by scientists for scientists, and I think that's still the primary focus. I don't know the exact breakdown of the participants there. Open source is very much on a scratch your itch kind of basis. People come in when they need to change something. So we don't have a lot of control over who pitches up. Unfortunately, we also don't have a lot of ways currently. We're working on it, but we don't have a lot of ways to enable people to participate who don't have that privilege already. So, some people can work on it as part of their jobs. Other people just can't do that. Um, so yeah, I would say that we see less involvement from industry and mostly still scientists and people who use these tools on a day-by-day basis. And then, of course, often people get hooked and they stay for longer than they intended to, many years longer sometimes.
So presumably a lot of these people are graduate students because they're the ones who
When they
have the
start
time
out.
to write the tool.
Yes. Yeah, they start out when they have a lot of time and then they get hooked and then they stay much later.
And do you have problems, significant problems with people? You said people arrive because they have a specific need, but I'm assuming the image processing community has a similar problem to us in that not that many of us actually have a good background in software development. So do you have problems with people who arrive and want to contribute and you find that they just don't have, they don't want to write documentation, they don't want to write unit tests, and it's an enormous struggle to get them to comply with good coding practices?
I guess that happens from time to time, but overall, once you've established a culture in a project, I haven't seen people try very hard to subvert it. Ultimately, you won't get very far because the community have decided that they want to set this high standard, and they won't integrate to changes without it. But that said, we often have people with very little experience arriving, and to us that's perfectly fine because it's more about your willingness to participate and being part of the whole process. We love bringing new people on board. We absolutely enjoy talking to enthusiasts, whether they're experienced or not. And I think that's one of the most the magnificent aspects of this ecosystem is that we've trained so many people to be good at their jobs also, but at the software development aspect. Most of us arrived here knowing very little about software development. I could code when I arrived. I didn't know what a unit test was. I didn't know how to write documentation, any of these things. It's all skills I picked up along the way, and I learned from the best people out there because open source tends to attract these people who are just really good at what they do. And they, at least in the scientific Python ecosystem, there's a great willingness to take that knowledge and share it with everyone around.
Right. I see someone has their hand up. I'm just scrolling. If you have your hand up, please just ask the question. I still haven't found your name in the list. Venkat, go ahead.
Hey, Stefan, very nice talk. So I have not, maybe this is a question related to Scikit image, and I've not really maybe kept in touch with all the latest, but for example, you've written all this code. Is there a migration towards like having more GPU support? How does that work also? Like, is there any, how do you handle the fact that there's always new hardware being developed, and what is that? I mean, how have you handled it or plan to handle it with Scikit image?
Yeah, thanks. It's a good question. Yes, it's challenging because inherently on some ways we are kind of conservative in how we move forward. Like we're reliant on volunteer labor, so we don't typically do drastic changes of technology over short time spans. That said, there are many interesting ways in which these experiments can happen outside of Scikit-image itself. And what we've seen in open source happen is that projects like scikit-learn and scikit-image, they're very good at figuring out the right APIs for things because you have people coming in using these things, iterating on them, and you have the whole community's input. So you can define the language of the computation very well. And then once that is out there, exactly how that is implemented, you can decouple a little bit. And so we've seen, for example, that NVIDIA and Intel and some companies have put resources into implementing these same interfaces, but for their specific hardware architectures. So there's like the Rapids project out there, for example, or Dask Image, and all these groups are trying to replicate some of these image processing functionalities for specific hardware platforms. And that's perfectly fine with us. We like that experimentation. And then at some point, there's going to be a solution. Someone's going to figure out a way in which this works. And what I mean by works is it won't disrupt too much what we have already, because remember what I said during the talk, it's very important to us that we're able to onboard people easily, that people can read the code, that they can see what's going on underneath the hood. And if you have too complex an underlying technical infrastructure, that becomes hard. So at some point, someone is going to figure this out, like a jump that was made with Python when someone figured it out for the first time, or maybe Numba, or one of these tools will figure out how to do GPU acceleration, and we'll build the interfaces and integrate with that. For now, we've experimented with some of them, but we haven't decided as a community to make the decision. It has been proposed, and every time we've stepped back from the precipice. So it's coming, but the community will have to decide when.
Thank you.
Thank you, Stefan. We are running a little behind now, so I think we should move on to our last speaker of the session. Can we switch over to Dora?
Thank you, everyone.